Welcome to lesson 2 for chapter 10, year 2 pure mathematics, and this is all about numerical methods. And today we're going to look at iteration. And you may have done iteration before. We're going to use it to approximate solutions to equations, particularly of the form f of x equals 0. So these are the roots of the equations that we saw in the previous lesson. Okay, so what I recommend you do, if you pause the video, try the 4 warm-up questions, and then we'll be ready to start. Okay, and let's have a look at the solutions. Okay, so question 1, there's 2 parts. The first part, we have to sketch the graph of the function f of x is equal to the square root of x. So this is a standard function, if you like. To get the curve just right, obviously if you take x is 0, we just get the square root of 0, which is of course 0, and then all the positive numbers will be well defined. So it's going to be a curve something like that, which flattens out a little bit. If you'll recall, if you're not sure how to define this, just remember that if you have a function f of x, in fact, I won't use f of x. If we have a function g of x is equal to x squared, then the inverse function g to the minus 1 of x will, of course, be the square root of x. And you can get there just by using a few steps, by obviously setting y equal to x squared, swapping the variables, and then making y the subject. Now, if the reason I'm saying that is because if you look at g of x as a function, it's the x squared function. It's going to go something like this. And then one of the key properties of inverse functions is that they are symmetrical about the line y equals x. So there will be a line of symmetry right there. Other ways to get there as well, but that's probably the main one. So that if that was the line y equals x, of course, this curve would be y equals x squared, and the orange curve is the one we're talking about. So this would be y equals the square root of x. Now, another thing just to bear in mind with the square root of x, if you're subbing in x values, which are of course negative, you're not going to get any real solutions. So, for example, if we take the square root of minus 1, putting a negative number in is not going to have any real value. So it has no real value. It does have an imaginary value. It's I, but that's on a different course. Okay, so the domain, we can now write down the domain and the range. So because we can't sub in any negative numbers, our domain is limited to just the positive x values, including 0. So we'll just write that down. So the domain of f of x, so f of x is only defined, sorry, let's do the domain first. So x is only defined for numbers greater than or equal to 0, but you can have, of course, real numbers. Okay, and it's in the broadest possible sense. And the range, of course, likewise is going to be positive, because the notation that they're using here in the question specifies that this is a positive square root. I just want to spend a bit of time talking about this. The function that is not well defined is when you take plus or minus the square root. Okay, we talked about this in the functions chapter. Because you have to stipulate that a square root is either positive or negative, that indicates that the square root function on its own, as we've got here, is the positive one. Okay, by definition. Okay, the negative one would be something else. You'd have to put the minus sign in front of it. So that means that if it's a positive function, the square root, although it's not well defined when you take plus or minus, what that means is that the range is going to be purely positive as well. So the range is all the positive values of y. So we'll just write those down. So that was the domain. I'll just make a note of that. And the range So y values again greater than or equal to 0, and any real number is allowed as well. Okay, so I hope that makes some kind of sense. Now, moving on to question 2, we're asked to sketch the graph of the following functions on the same pair of axes provided. So we've got the square root of x plus 1. Now, if you just remember from the previous question, we had f of x was equal to the square root of x. So the input is x into this function. So if we change the input, to x plus 1, like that, we get the square root of x plus 1. Subbing in like with like. Now that means that g of x is, of course, f of x plus 1, as I've just defined it. And that is a translation of f of x. So because it's f of x plus 1, that means that I have to shift my graph 1 unit to the left. Okay, I'm just thinking aloud, well, thinking my thoughts on the board here, and the kind of things that you should be probably thinking when you're sketching these things. So we'll sketch the graph. It's the same curve, it just has to be translated by 1 unit to the left. So I'll put it something like that. So this is going to be y is equal to g of x. Okay, and it will be of a point of contact with the x-axis at -1. Okay, now for h of x, that's just the graph y equals x. So I can put that in pretty easily. We've done it already. So it's just going to be the straight line passing through the origin, the gradient of 1. So just label that as well. So this would be y is equal to h of x. All right, now h of x is defined for all real numbers. That's no problem. And you can see there is one point of intersection. And this is something to anticipate when you're doing questions like this. If you're asked to sketch graphs and they're clearly going to intersect, expect to maybe write down the number of solutions in the next part of the question. And that's exactly what we're going to have to do here in 2 part B. So it says write down the number of solutions to the equation x is equal to the square root of x plus 1. Well, that is simply where g of x is equal to h of x. Which is where I've labeled already. So there is only one solution to this. Okay, they're going to diverge after that point of intersection, and then we also can see that g of x is not defined for any x values less than -1. Okay, and that leads us on to our third part of the question, which we'll do in a second. So we've just got to write down the number of solutions. Well, there is, of course, just one solution. Okay, now just to scroll down a little bit, for part C, it says write down the domain and range of G. So I'm just going to put that back so it looks a bit more accurate on the graph, the domain and range of G. Well, G, from our diagram, and I've alluded to this already, so the domain, this is for part C. So any x value greater than or equal to -1 is absolutely fine. That's where G is defined in its domain. -1 is allowed as well, because if you put -1, you'll just get this -1 plus 1, which is the square root of 0, which is, of course, 0. The range is going to be the same as the range for f of x in the previous question, because it's just a horizontal translation. So the range is simply going to be y values that are greater than or equal to 0. Okay, so that's the first 2 questions completed. Okay, for the next question, question 3, we have to show that the equations x equals the square root of x plus 1 and x equals 1 over x plus 1 can be written as the quadratic x squared subtract x subtract 1 is equal to 0. Well, if we start off with the first equation, I'll call this one big A, and we'll call this one big B. So starting with big A, what can we do? Well, if we have x is equal to the square root of x plus 1, what is immediately striking is the square root. We need to undo that square root symbol, and we can do that by squaring both sides. So therefore, if we square both sides, we get x squared is equal to x plus 1. Okay, now we need to create a 0 on the right-hand side of the equation, and we can do that by subtracting x and subtracting 1 from both sides. So we have x squared subtract x subtract 1 is equal to 0. Okay, so that doesn't seem too bad. Now moving on to B, let's see what our starting point is. Well, we have x is equal to 1 over x plus 1. Now, the thing that sticks out in this situation is the fact that I've got an x in the denominator. Okay, right here. Now, I need to remove that denominator because we don't have any fractions in our equation. So I'm going to multiply everything by x. So therefore, I'm going to have x squared is equal to 1 plus x. And now again, I want to create a 0 on the right-hand side. So by doing that, I have to subtract subtract 1 and subtract x from both sides. So therefore, x squared subtract x subtract 1 is equal to 0. And we've got the same result. Now, for part B, it asks us to use our calculator to write down the exact solutions to the equation. Well, if we write down the exact solutions, we can use the equation solver on our calculator. So I'm just going to go down to the menu option A here. So polynomial degree 2. All right, and then we put in the coefficients. Now, obviously, it's x squared, so 1x squared, -1 for B, and -1 for C. Now, let's see what we get here. Press equals 1 plus root 5 over 2. Excellent. Does anybody recognize this number? Okay, something for you to Google perhaps. So solutions. So we'll say x1 is equal to 1 plus root 5 over 2. And you can probably guess what the next solution is going to be. It's the quadratic formula, isn't it? So x2 is 1 subtract root 5 over 2. So x2, second solution, is equal to 1 subtract root 5 over 2. Okay, so those are the exact solutions. When it says exact as well, just so you're aware, it means leave it in surd form, okay? What you don't want to be doing is pressing the equals button or the SD button and converting it into a decimal. That's not what's required. The exact value should be, if it's an irrational number, it should have surds in it. Okay, now for question 4, we have a sequence A1, A2, and A3. We've got A1 as 1.6, and we have what looks like a recurrence relation going on. So we have to find A2, A3, and A4, and we're giving our answers to 3 decimal places. So we're going to use the calculator again. So we'll just cancel that and we'll drag it over to the other side, and we'll just clear all this work. So to get all this set up, let's just write down what we know, and then we can deduce what A2 and A3 and A4 might be. So we know A1, that's given to us, is 1.6. Now, the recurrence relation states that if I sub in from here n equals 1, we can start with n equals 1. Then if you replace the n with 1 wherever you see it, so there and there, we're going to get A2 defined for us. So you just follow the instructions. So A2 is going to equal 1 over A1 plus 1. Okay, so that means it's going to be 1 over A1, which is, of course, 1.6. And then we're going to add 1 to that. All right, that's going to generate an answer. Now, I'll show you how to use your calculator in an effective way for using these recurrence relations. So if we put in 1.6 first of all, so let's go to mode 1, 1.6, press equals. Okay, you can change it to a decimal if you like. Now, what we can do is we can now put in the recurrence relation. So the recurrence relation says that you take 1 and then you put that over the answer, which was the 1.6. We come out of that and then add 1 and press equals. We get 13 over 8. So that's the next value. So I'm just going to write that down. So that's 1.625. Now, for when n equals 2, this will generate a 3, which is 1 over A2 plus 1. So it's the same rule. Now, on your calculator, and I'll just write down the working out. So it's going to be 1 over 1.625 plus 1. Now, because on your calculator, we've got 1 over the answer plus 1. If I just press equals again, it will generate the next term for me. So that's going to be 21 over 13. So it's going to be 1.615. Now, we're asked to give it to 3 decimal places where appropriate. So I'm going to have to round this one. So this is 1.615 to 3 decimal places. Okay, so we've got a 3. Now we have to do one more. So when n equals 3, this will generate a 4 for us. Okay, and I won't write it all out again. We're just going to press equals again on our calculator. Okay, change that to a decimal, and we get 1. Oops. Go back to the right function. So that's going to be 1.619 to 3 decimal places. So we have a series of answers here. We had started with 1.6, then we went to 1.625, 1.615, 1.619. Now you could keep going and going and going with this, and just out of interest, it's if you just keep pressing equals on here, it's going to go further. So that's as far as I'm still pressing equals. That's about as accurate as my calculator will allow. So it seems to be converging on about 1.618. So more about that later. We're going to be using iteration quite a lot in this lesson, and we're going to be sort of taking it into new places. Okay. Anyway, that concludes the warm-up. So let's get into the main meat of the lesson on iteration. So iteration, which you have met before, is a method. So it's an iterative method, as we call it, and for iteration, can be used to find a value of x for which f of x equals 0. All right, and equations you can usually set up so that they're equal to 0 anyway, even if they're not initially written in that form. And we can demonstrate this method using an example. So we're going to go back to the example that we saw in the warm-up, okay, which was the equation x squared subtract x subtract 1, which which will give you a value which is called the golden ratio. You may have heard of it. So the first thing we need to do is we need to rearrange the equation. So we're not going to solve this equation using the quadratic formula. It won't factorize, but we can use an iterative method, which is what we're going to focus on today. Now, there's different ways of doing this, or there's different approaches initially, and usually you'll be given an iterative formula to use. But what I've decided to do is we're going to actually create the iterative formula ourselves. And the first step in doing this, which we obviously called in step 1, is we rearrange the equation and we arrange it so that it has the form x is equal to g of x. So x is equal to some function of x. Now, turns out there's 4 ways we can do this. And you've done 2 of them backwards in the warm-up. So for example, and you'll see what I mean, we'll do A1 first. If I write down the equation, so we have x squared, subtract x, subtract 1 is equal to 0. My aim is to make x equal to another function of x. So I need to keep 1x on the left-hand side of my equation and then put everything else onto the other side of the equation. Now, one way I can do this is, assuming x is non-zero, I can just divide through everything by x. Okay, now if I do that, I'm going to divide every single term by x in this instance. So if I divide that by x, divide the second term by x, the third term by x, and obviously I'd have to divide the right-hand side by x as well. Okay, and we'll just put a little caveat in there. So assume x is not equal to 0, otherwise that's a naughty thing to do. All right, now what happens here? Well, if we do x squared over x, that's going to give us x. Then we're going to get 1. Then we're going to get 1 over x, and we're going to keep the 0 on the right-hand side. Okay, now what I can do is I can keep 1x on the left-hand side and move everything else over to the right-hand side. So the x I'm going to keep is this one. Okay, and if we add 1 and then add 1 over x to both sides, we're going to get the following. So we'll get x is equal to 1 plus 1 over x. And that's in the form we want, because we want x is equal to some function of x. So in this case, the g of x would equal 1 plus 1 over x. Okay, so that's our first iterative formula, and I'll just highlight that to make it stand out. Or, well, our first rearrangement anyway, which would lead to an iterative formula. Okay, now for A2, I've taken the first step for you because I want to lead you into a particular direction. We're going to look at this in more detail in a minute. So what I've done is I've added the x and the 1 and 1 to both sides, and that would clear the negative x and the negative 1 on the left. So all that remains now is to make x a subject. I'm going to take square root of both sides. So if I take the square root of this and the square root of this, we're going to get x is equal to the square root of x plus 1. And we'll just take the positive root for now. Okay, now the third way we can do this, so again, I'm just going to write out the equation again. So x squared subtract x subtract 1 is equal to 0. I can use a factorization. But first, I'm going to add 1 to both sides. So we're going to have x squared subtract x is equal to 1. And then I can factor out an x on the left-hand side. And what I'm left with is going to be x subtract 1 is equal to 1. And when I do that, I can divide through by the x subtract 1, and I'm going to get this. Okay, so we now have 2 more equations. So we've got this one, which is A2, and A3, which is x is equal to 1 over x subtract 1. And notice they're all unique, okay? Now, the fourth way to do it is probably the easiest one. I've saved the easiest one for last here. We've been doing stuff with the x squared quite a lot. So probably the most obvious way to do it is to start with the equation first of all, and then just add x to both sides. Now, if you do that, we're going to get x squared subtract 1 is equal to x. And again, that's in the form that we wanted. So if I just write it the other way around, it's going to be x is equal to x squared, subtract 1, like that. And we have yet another equation of x written in the form that we want. So why is this useful? Well, for the next part, we're going to, as it says here, we're going to take a closer look at A2 and see how this will help us find the solutions iteratively to our equation x squared subtract x subtract 1 is equal to 0. So I've just zoomed out a little bit just to get everything in onto the screen. We're going to have a look at the plot of y equals x and y equals the square root of x plus 1. What that will allow us to do is to show visually how to generate the solution for the equation x is equal to the square root of x plus 1, because as you can see, if you plot the graph y equals x as I've stipulated here, and the graph of y equals the square root of x plus 1, setting those equations equal to each other will produce this solution, hopefully, which is the golden ratio, 1 plus root 5 over 2 to be exact. Now, we're going to use an iterative method to do this, and we'll sort of start looking at the iterative formula, how to generate the solutions, and then we'll see how to show this graphically on the graph that we've got here. Okay, so for the iterative formula, it's actually really easy. We know that we have x is equal to the square root of x plus 1, which was our A2, our rearrangement of the equation. I'll just make a note of this. From a rearrangement of x squared subtract x subtract 1 is equal to 0. Now, to create the iterative formula, we can use this format. So the x that is as not as a subject but is on the left hand side, we set that as x with the subscript n plus 1, and then the x terms on the right hand side we use the subscript n. So in our example that we've got here in our A2 that we were using, the iterative formula is simply going to be x with the subscript n plus 1, and on the right hand side this is going to equal the square root of x with a subscript n and then plus 1. Okay, and all that is square rooted, so I'll just continue that. So that's our iterative formula. Now it says choose a suitable starting point. There'll be more, there'll be more about that later on. But obviously if we choose what I've decided to use, which is 0.4, as you can see here, if we use that as a suitable starting point and we sub that into our equation, well, let's see what we get. And we're going to do this on a calculator and generate multiple answers over and over again in an iterative manner. So if we set x0 equal to 0.4, and just to make it clear as well, I didn't stress this earlier, the iterative formula is valid for when n is greater than or equal to 1, n being a natural number. So if we put x0 as 0.4, then our x1, okay, so x1 is just going to be the square root of 0.4, just plug that in. In fact, let me just go back a step. That's going to be the square root of x0, I should say, first of all, plus 1. And that's going to equal the square root of 0.4 plus 1. And we can do this on our calculator. So if we plug all that in, we're going to take the square root of 0.4 plus 1 inside the square root, just come out of the square root there, and we get an answer, root 35 over 5. We'll put that as a decimal, so that'll be 1.183. So that's equal to 1.183 ... Now, That's our x1 value. So I'm going to write that on in this box here. So that's 1.18. Excuse me, not done that correctly. It's 1.183 ... Now, to generate x2 and the rest, the iterative formula now comes into play. So for x2, that's simply going to be the square root of x1 plus 1. Okay, and that is obviously equal to the square root of whatever x1 was, which is the 1.183. That's obviously rounded, plus 1. Take the square root of all that. Now, it's obviously quite crude doing it like this because it's clunky and we're rounding our answers. I don't want to round the answers. So now I'm going to create an iterative formula on the calculator. So now that we have our x1, we can now say, so if I punch in the function again, but I'm going to use the square root function, and then I'm going to use the answer key, okay, and then plus 1. Now, if I come out of that, that will generate x2 and then x3 and so on without doing any kind of clunky calculation. So if I press equals, that's going to be my next value. So that's going to be 1.14775 and so on. Again, it's going to go on and on and on. So we'll put that as x2 right here. We'll just do 3 decimal places, 1.478, I suppose. And I've just realized I've put an extra 1 in on there, which I shouldn't have done. Let's just rectify that. So it should be 1.4775. My apologies there. Okay, so that's x2. Now to get x3, without doing all that clunky work, I just press equals again. There's the next one. So this is going to be x3. Which is 1.574. Okay, we'll keep it like that. Now let's do x4. Just press equals again. Just write that down. That's going to equal 1.604. And then you can just keep pressing and pressing. So I won't write any more down, but if you just keep pressing until the calculator. There we go. So we seem to have settled on 1.618033989. So that's as good as it's going to get on the calculator. Now I want to show this process visually. Okay, so we're going to go back to the graph, and then we're going to show how these inputs converge on a particular value. And remember, the solution is where the graph of y equals x and where the graph of y equals the square root of x plus 1 intersect. Before we get started with the diagram and showing how the iteration process converges on the roots diagrammatically, what I just want to explain is something of probably a little error that I've just been talking about, and I don't want a misconception to creep in. So when we're setting up the iterative formulae, I stated that you can use n is greater than or equal to 1. Now, that would be the case if the iterative formula was written in this format, where you use xn for the new term and xn minus 1 as the previous term. Now, simply because if you substitute in n is equal to 1 as the first valid entry, you would generate x1 is equal to the square root of x0 plus 1, which would indeed work because we know that x0 is, of course, 0.4. So where the mistake crept in was the fact that I said that an iterative formula defined as the one above, so like this, where you have xn plus 1 and xn, that would actually be valid for n is greater than or equal to 0. And simply because if you sub n equals 0 in for this, you're going to get x1 again is equal to the square root of x0 plus 1. Okay, but it doesn't matter which one you choose. You could either use this one with n and n subtract 1, but you'd have to use n is greater than or equal to 1, or you could use n plus 1, n, and then you can use n is greater than or equal to 0. Okay, so as long as you're consistent, it doesn't really matter. On the class whiz as well, I've just made a note of this. When you work out the first term, you're plugging in the x0 right here. Okay, and then you'll get an answer. Press equals, and then you'll get an answer. That answer you can use in your next iteration, and then if you use the answer button, it will just generate more and more terms, so you don't have to write all the working out again and again and again. Okay, so to show this diagrammatically, I'm just going to make a little bit of space. This might encroach on my space, I don't know. So how does this work? Well, our first input is, of course, x0, which is 0.4. So that's the first x value I'm going to sub in, and that will generate a y value. So let's do that. I'm going to use green, I think. So we're going to use a straight line. So for 0.4 as my first x value, reading that off, this is x. This is the line x equals 0.4. And if I go up to my graph for the square roots of x plus 1, it's going to be about there. Just gone a bit wonky. Now, you'll notice that if you read off on the y-axis from where that is, it's about there. I'm not going to add any more lines. So that's going to be about 1.18. It looks about right, doesn't it? Yeah, the one just a bit less than 1.2. So that seems to check out, which is good. So that looks good. Now, what comes next is the fact that this 1.18 that we've just discovered by putting it into the function is going to be my next x input. So I have to find this 1.183 on the x-axis and generate the next input. Now, to do that more accurately, rather than kind of fumbling around and trying to find it over here, it's going to be around here somewhere, isn't it? What I can do is I can use the line y equals x. Now, if I just draw another line horizontally this time from that point across to line y equals x, it will take me straight to the x value that I need, which is 1.183 right there, and it will read off exactly. So it's about there, isn't it? And it takes me straight to it, which is really good. Okay, now that's my next input. So my next x input, I need to take that value to the function because we're going to plug that x value into the function. So we're going to go from 1.18, we're going to plug that into the function. So I go up to the curve, and that's going to take me to a value somewhere between 1.4 and 1.5. And again, that seems to check out. It's what I've got here. Okay, now that's going to be my next x input. So I'm going to take that value, I'm going to plug it in as my next x input. So I'm going to use the line y equals x again to find it on the x-axis. So it's going to be about there. Just reading it off. So somewhere around here. So it seems to be correct. And then I'm going to plug that into my function. So let's do that. So if I plug that into my function, it's going to generate a value on the curve, which is about just a bit less than 1.6. So 1.57 looks pretty good. So again, that checks out. I'm just going to tick that off. So that looks good. And then we repeat this process over and over again. And you'll see what's going on here. We start at the x value 0.4. We read it off as the new x input using the line y equals x because it converts your y value into an x value. That's what y equals x does. And then we input it again, takes us to the curve again. Then we read it off. Then it takes us to the curve again. And if we keep doing this process, so I'll do a couple more. We read off that value. We take that to the curve. It's converging on my root. Now, I probably can't do much more than this graphically. So about there, I'll do one more. You can just about see it, but it looks like I'm tending towards my root. Okay, so it's converging on my root. Now this is called a staircase diagram. And again, it's an exam requirement. Okay, so this is called a staircase diagram, and it's showing graphically how iteration converges on the route that you're trying to find. So before we look at the worked examples, I'd like to just have a look at A3 and A4, which were the two equations that we formulated earlier. Now, I've generated iterative formulas for A3 and A4, as we saw in the previous example. And we're going to do this purely graphically. We're going to see if we can converge on the solution to the equation. So the solution to the iterative or to the equation x equals 1 over x subtract 1 appears to be here. So it's a negative root. Okay, and similarly for A4, we have the positive root there, so that's just over 1.6, which is the golden ratio. All right, so you'll find this happening in some instances, depending on which iterative formula you use. Remember, there's 4 to choose from for this particular equation. It may generate one of the roots, it may generate another root. Okay, and we'll see that it won't always work. All right, so we'll just go through the thought process of how to do this relatively quickly. So we'll start with A3, and we've got the iterative formula here. Now, we don't really need to worry about that too much because we're going to use the diagram to guide us. What we are interested in is this starting point here. So x0 as equal to -1. So if I start with that, and I strongly suggest you use a pencil and a ruler for this. I'm going to do it in green. And the process is as follows. You start by drawing a line to the curve. So I'll just make a note of this. So you go curve, then you go to y equals x, then you go to the curve, then you go to y equals x, and it's simply horizontal, vertical, horizontal in that fashion. Okay, and so on and so on. So it just keeps repeating in that fashion. So if we go to the curve, this is going to be a vertical line. So starting at x0, which is -1, right here, that's my starting point. So I'm going to draw a line from -1 to the curve. So I'm going to the curve first of all. Okay, now I've gone to the curve. I now have to take my line to y equals x as stipulated right here. So I go to the y equals x now. So I'll keep the same color. So from the curve, from that point, I go to the line y equals x, which is the dotted line. Okay, now the process states that I now have to go back to the curve. Now the curve is directly below, so I'm going to go down. Okay, so just to reaffirm what I've just said. So going to the curve, vertical, going to y equals x, horizontal, vertical, horizontal, and so on. So we've now gone vertically to the curve. We now have to go horizontally to the line y equals x. So that's going to take me to about there. Right, now I need to go vertically again, back to the curve, which is there. Then I need to go horizontally. Then I go vertically. Then I go horizontally, vertically, horizontally, and so on. And I don't think I can get any more on there. So this is rather good. Now, what this has done, this is converged, but in a different kind of way. Now, this is you'd think this would be called a spiral diagram. Now it's not. This is called a cobweb diagram. So just make a note of that. This is a cobweb diagram. Again, it's an exam requirement to be able to use one of these. And that shows convergence in the same way as a staircase diagram does. Okay, so that's using x naught is equal to -1 as a starting point. Now, you could use other starting points if you chose. I suggest you try it. I won't do it here. Try some different starting points, like minus 0.2 or something, and see if you still get the convergence. Now, moving on to A4, we have a different iterative formula and a different starting point. So let's get straight into it. We're going to be starting with 1.8. So I need to locate that. And we go from 1.8 straight to the curve. So I'm going to use green again. So 1.8 on the x-axis is right there. In fact, I've just missed it. Let me just highlight it so you can all see it. So 1.8 is there. Now let's try again. So I've got to go to the curve first of all. Right, okay, so I've gone to the curve. Now the instructions say I have to draw a horizontal line to the line y equals x. Now that's on the right-hand side, so I've got to go this way. Okay, that's going to generate my next input. Now I go vertically to the curve, so I've got to go straight up. Okay, now I go horizontally to the line y equals x, and I've gone off the screen essentially. So this doesn't seem to work. Now, if I just put some arrows on here as well, we started at 1.8, we went horizontally, we went vertically, went horizontally. This diverges. But to be more blatant about it, this does not converge. Now, some iterative formulas will not converge at all. And you can show this on the calculator as well. Okay, if you want to show that something does not converge, you'll see that the numbers will just become out of control. They will get bigger and bigger and bigger until your calculator cannot cope anymore. All right, so I can just show you this very briefly. Okay, so I've just plugged in 1.8 as my starting value, and I'll just erase this so it's just not obscuring the calculator screen. Then if I set up my iterative formula now, the iterative formula here says I have to square my previous value and then subtract 1. So if I put that in, so it's going to be answer squared subtract 1. Okay, let's see what happens. So I'm going to press equals. That generates my next point, which is 2.24. And as you can see, that's pretty accurate on the diagram. Okay, so that's 2.24. That's pretty good. Now, if I just keep pressing this, okay, we're just a few presses. I'm now at an incredibly large number, and I don't think my calculator can cope anymore with that. So that's divergence, okay, and it will not converge on the root. So it either depends on the iterative formula or your starting point. So once again, you might want to try some different starting points for this A4 example and see if you can find any convergence. So worked example 1, we have a quadratic equation. We have to show in part A that the equation f of x equals 0 can be written in that form. So first of all, let's set up the equation equal to 0 as it's given. So for part A, if we just say that f of x is equal to 0, then what that means is, of course, that x squared subtract 4x plus 1, sorry, is equal to 0. Now then, it can be a little bit confusing as to know where to start with this because we have to show it can be written in a particular way, but we've seen from the previous ideas that you can rearrange these equations, you can get 4 variations of it. So a good idea is to just look at what you're aiming at, which is right here. I'm just going to highlight it and work backwards. So I'm going to do a bit of rough work here. So we just call this rough work and let's go backwards. So if we start with the x is equal to 4 subtract 1 over x, then the first thing that leaps to mind, I think, is the fact that we've got this x in the denominator on the right-hand side of the equation. I don't really want that. I think I'm going to have to multiply by x. And what I'm trying to do is I'm trying to get back to that original equation that is stated here. Okay, so if we multiply everything by x, we're going to get x squared is equal to 4x subtract 1. Now, I think that's given us enough information. If we work backwards, we can see that our first aim, now that we've written f of x equals 0 as the quadratic, what I really want to be doing is making the x squared part here the subject of the equation. Now, I actually said that wrong. What I meant to say was the x squared should be left on the left-hand side by adding 4x and subtracting 1 from both sides. So let's do that now. So going back to our question, we can see that if we make x squared I keep saying that, we leave x squared on its own on the left-hand side, add the 4x, we're going to get 4x and then subtract 1. Okay, and then we have to consider, how do we generate that 1 over x and that 4? Well, we divided by x. So by dividing by x, I'm just going to write it out again and show that we divide by x term by term. So x squared divided by x is equal to 4x divided by x, subtract 1 divided by x. You have to do it to every single term to be consistent. So therefore, x will be equal to 4 subtract 1 over x as required. Okay, obviously x cannot equal 0. That's why it states it here, because you can't divide by 0. So that's part A. Now for part B, it says that f of x has a root in the interval 3, 4, 3 and 4 not inclusive. So another way to write that interval would be to write it like this, so it looks like a pair of coordinates. So we're told that it has an interval root in the interval 3 and 4. Now, to use the iterative formula that's given with x0 equals 3, we have to find the values of x1, x2, and presumably x3, which is hidden by the calculator. Okay, so for part B, we've got the iterative formula. We've got our x0. Okay, so x0 is 3. That's given to us. Now, to generate x1, we simply use the previous term. So it's going to be 4 subtract 1 over x0, which is the same as 4 subtract 1 over the 3 that was given to us, all provided for us in the question. So if we work that out, I mean, you'll know what this is anyway, but we'll just put it into the calculator because we're going to use it in a moment. So mode 1, 4 subtract 1 over 3, and just come out of that. And that's going to give us our x1, which is 11 over 3. And you can convert that into a decimal if you like. So that's going to be 3.6 recurring. Okay, so that's our x1. Now, without clearing the calculator, we can now set up our iterative formula on the calculator. So the way to do that, I'm just going to make a note here. So what we need to do is look at the formula. Well, it's x is equal to 4 subtract 1 over x. So we need to create 4 subtract 1 over the answer. And that will give us our iterative formula. So let's do that now. So 4 subtract 1 over, and then press the answer key, just come out of that. So we've set that formula up. Now if we press equals, this will generate the next term, which is going to be x2. So we can write that down. So using ClassWiz, So we now know that x2 is equal to 3.72 recurring. Okay. And to get x3, compress it again. That's all you have to do. That's 153 over 41. Just convert that into a decimal. So that's going to be 3.73. Now, I'm just going to check the accuracy that we need here. Doesn't say, so I'll just round it to 3 decimal places perhaps. So it's 3.731 or 732. Okay. So we're kind of confirming that there is a root between 3 and 4. If you keep pressing your equals on here, okay, that the calculator kind of stops there. So it seems to be converging on 3.7332. So that might be what the root is. I'm pretty confident about that now. Another way, of course, is to use a quadratic formula to solve it, and you'll get the exact answer. But the iterative formula has done the job to the accuracy that whatever accuracy require, in fact. Okay, so that's worked example 1. Now, worked example 2, we have a function f of x defined for all real numbers. It's got an exponential function in it and a linear component as well. So this is an example of an equation you could not solve algebraically because it mixes polynomials with what we call transcendental functions, things like e to the x, sine, cosine, that kind of thing. So this is our function. Now let's see what we can do here. It doesn't mean we can't solve them. We just have to use numerical methods like this. So we're told it has a single root at x equals alpha. Now, our first job is to find an iterative formula in essence, really. It doesn't say that explicitly, but we're asked to rearrange it. So it says show that the equation to find alpha can be written in the form x is equal to the natural log of 5 subtract x. Well, I'm just going to use the space up here because you've got the line space down below. Just so I can keep the question in front of us. You can see that the equation to find alpha is correct because we have f of x is equal to 0. Okay, and that x in this instance would equal alpha, the root that we want. So how do we rearrange it in that form? Well, again, a good idea would be to do a bit of rough work here. Okay, so I'm gonna work backwards. So I'm going to start with x is equal to the natural log of 5 subtract x. Now, obviously there's no natural logs in f of x whatsoever. We do have an exponential function. Now, the way to undo the log, as you know, we need to use the inverse function of a log to get rid of the log, which we can't see in our original equation, f of x equals 0. So if we exponentiate both sides like that, we'll get the following. So we'll get e to the x would be equal to e to the natural log of 5 subtract x. And we're going to use the idea that e to the natural log of x is just x because e and natural log are inverse functions. So that simplifies, so therefore we're going to have e to the x is equal to 5 subtract x, because if you haven't spotted it, the 5 subtract x is your input, and here in what I've just said, when you have any input, e to the natural log of your input just returns your input. Okay, so that's just going to return us to the 5 subtract x right there. So that's a really good clue as to what to do. So for part A, So the solution will run as follows. So we can see now that we need to make e to the x the subject of the equation. So if we start with e to the x plus x subtract 5 is equal to 0. We've done the rough work. We now know that to make e to the x a subject. So therefore, e to the x is going to equal, subtract x and add 5 to both sides. Okay, now to create the log, we're going to have to take logs of both sides. So we're going to do the natural log of e to the x is equal to the natural log of 5 subtract x. Okay, we can use the power law for logarithms now. So the x in the power can come down to the front. Like that. So it becomes a multiplicative variable. So let's write that in now. So we're going to have x log e is equal to the natural log of 5 subtract x. And as you should be totally and utterly well aware now, the natural log of e is just 1. So there we have it. So we have x, therefore x is equal to the natural log of 5 subtract x as required. Okay, so that's part A. Now for part B, we're told that the curve with the equation y is equal to 5 subtract x meets the line y equals x at a single point. And you'll be able to see this on the diagram as well. Okay, we're going to use the diagram momentarily. But what we first have to do is show in part B that there is a root, or the root alpha lies between 1 and 2. So remember, alpha is the solution. So we know that e to the alpha plus alpha subtract 5 is equal to 0. Okay, we know that because alpha is that specific value that makes that equation true. So how do we show that alpha is between 1 and 2? Well, we can use the theorem that we looked at in the first lesson, and we're going to look for a change of sign between 1 and 2. Okay, so if we're showing a root lies between an interval, let's plug in those numbers. So for part B, which I'll do here, consider f of 1. Write that in. So f of 1 and f of 2. So you might be thinking now, well, hang on, how do you know this is the correct root? Well, we use the information provided in the question, don't we? We know it's the correct root because in the question it says that this function has a single root. It's the only root. Okay, so we know this is where alpha lives. Okay, so we know there's a root if there is a change of sign between f of 1 and f of 2. Okay, so we plug everything in. So therefore, f of 1 is simply going to be e to the 1 plus 1 subtract 5. And what do we get for that? Well, we can use our calculator. If you want to, of course. So this is going to be essentially e subtract 4. Now, you don't necessarily need to use a calculator here. If you know what the value of e is, it's about 2.7. So we know that 2.7 subtract 4 is going to be negative. Okay, so I can say with confidence, I'm just going over my diagram here, that is less than 0. So what I'm hoping for now is that f of 2 is going to be positive. So let's have a look at this. So f of 2, that's going to be e to the power 2, which is just a bit less than 9. Okay, so 2.7 squared essentially. Okay, plus 2, and then subtract 5, which is going to give us, again, I'm running out of space. I'm just going to go over here. So it's going to be e squared plus 2 subtract 3. Now then, e squared, like I said, is positive. It's just a bit less than 9. And in fact, if you just want me to convince you of this, I'll do it. So just get rid of that. Move this over. So use the e function, e squared, subtract 3. I hope you're convinced that this is very positive indeed. Yes, it's 4.389. Okay, but you can just say that that's positive if you like. Okay, so that's positive. So what we have here is we have a change of sign. Okay, now because we have the change of sign, so we can now say, therefore, alpha must lie between 1 and 2. Because the function is continuous, whether you know it or not, it is continuous. There is a change of sign in the function on that interval. So it's got to be continuous over the interval 1, 2, which it is. It's valid for all real values of x, so it's definitely continuous. There is a change of sign, so that means there is at least one root in that interval, and we know, we're told in the question, there is indeed one root. So continuing with the example 2, we're going to start using an iteration formula that has been provided. And we know how to generate these ourselves, don't we? So we've set the subscript of n plus 1 on the left-hand side and the subscript of n on the right-hand side. And we've got a starting value of 2. Okay, so we're going to plug in our starting value. We'll use a calculator simultaneously to do this. All right, so if we write x1, we've got the natural log of 5 subtract x0. So just note, of course, that the subscript here has to be 1 greater than the subscript here, and we can use the value of x0. So this is going to be the natural log of 5 subtract x0, which is 2. Is given to us, so don't worry about that, which is equal to the natural log of 3. Okay, now we are going to give our answer, it says to 4 decimal places, so if you want, just plug this into your calculator now. We've got x1, but we'll get it in decimal form. So we take the natural log, so natural log function, 3, close the bracket, so that's 1.0986. So this is approximately equal to 1.0986. Okay, it wants it to 4 decimal places in the end, but the calculator will maintain the accuracy for us. Okay, and that's to 4 decimal places. Now then, for x2, obviously, we use the iterative formula, so that's going to be 5 subtract x1. Again, using what we understand about iterative formula, the subscript there has to be 1 greater than the subscript there. So let's continue. So this is going to be the natural log of 5 subtract what we got in the previous answer. So that's going to be all that. So I'll put it in a different color. So that's going to be 1.0986. Now, obviously, it's quite crude doing it like that. So we're going to go to our calculator now. Now we have our answer on our calculator. We can set up our iterative formula on the calculator. So let's just think how to do it. So on our calculator, so we want to create the iterative formula. So it's simply going to be the natural log of 5 subtract the answer. Okay, hope that makes sense. So let's type that in. So leave the answer, just type over it. So just press natural log and then 5 subtract answer, close your bracket. Let's see what that gives us. 1.3613. Great, we can write that in. That's the 4 decimal places. And without doing too much more work, I've just forgotten how many terms we need to do. X1 and X2. Oh, we've finished anyway, so that's good. If you wanted to carry on, we can just carry on. Why not? Let's just keep pressing that button. Right. Okay. Oh, right. Well, that seems to converge nicely, doesn't it? Okay, but it's about 1.3. Okay, once you've done a few iterations. All right. So that's part C finished, and I didn't label it, so just label that. Okay. Now for part D, use the diagram to determine whether or not this iteration formula can be used to find an approximation for alpha. Justify an answer. So now I'm going to return to the diagram and we can see if the diagram does indeed show convergence. So this diagram is developed from derivative or it's not a derivative as such, but it's derived from the iterative formula that we've just been using. So you can see we've just set x on one side equal to the natural log of 5 minus x on the other side. And the solution is obviously where these two graphs intersect. So we're going to use the iterative process, but we're going to do it diagrammatically now. So if you remember from previous examples, so first of all, we draw a line to the curve, okay, which then goes to the line y equals x. Okay, and then we go to the curve again, and then to the line y equals x, and so on, back to the curve. Okay, and I won't do any more. And remember, the line to the curve is vertical, so it's going to go vertical, then it's going to go horizontal, vertical, horizontal, vertical, and so on and so on. So vertical line to the curve to start us off. Let's stick with that nice green color. So we're starting at x0 is equal to 2 right there. Okay, so it's for the iterative formula that we've just been using, and 2 is very kindly marked on the diagram. So let's start with that. So nice vertical line to the curve. So about there. You can use a pencil and ruler for this. Okay, now we have to draw a horizontal line to the line y equals x. So I'll stick with the same color. So I've got to go to the left this time. So it's going to be there. Now I go a vertical line to the curve and horizontal line to y equals x. Vertical line to the curve, horizontal line to y equals x, and isn't that nice? So it looks like we've got a really nice cobweb diagram in front of us. So we've got a cobweb diagram. And what that means is it converges. To our root alpha. Okay. So that's essentially it. So if you can show your diagram is a staircase diagram which converges or a cobweb diagram which converges, we've essentially got our solution verified.